Welcome. This is the first of two videotapes on the subject of Ethernet. Both tapes will be about an hour long. It's planned that the first tape will be the tape that most of you will want to see. The second tape will go into much greater detail. The material for both tapes comes from a talk given at the National Computer Conference in 1976 in New York. In fact, the slides that you'll be seeing in a moment come from that talk. And all of the material comes from a paper published in the Communications of the ACM in July '76, done by myself, Bob Metcalfe, and my colleague, David Boggs. Okay, now we'll go and we'll look at the slides, and you will find what the Ethernet's about. The Ethernet is a communications network developed at the Xerox Palo Alto Research Center by myself, Bob Metcalfe, and David Boggs. And before getting into the details of its operation, we'll spend some time, in fact, more of this tape than you'll think is justified, setting the background for Ethernet and the problems that it's intending to solve. This first slide attempts to organize a very complicated and somewhat new subject called distributed computing, in which you'll see the Ethernet is located toward the center. The idea here is that if you take all the modern computing systems and their associated communication systems, that you can organize them in a line according to some metric of their distance from one another or the rate of communication among them. Remote computer networking is the oldest of the three areas designated on this slide. It had to do with, and still has to do with, the connection of very large computers at great distance, say across the United States. And here are a number of systems which can be classified as remote computer networks. For example, the ARPA computer network, a network which connects fairly large machines like 370s and PDB-10s across the United States. Then there's the commercial version of the ARPANET, the Telenet Communications Corporation network, which is very similar. The Aloha packet radio network that I'll be mentioning again later. The TimeNet packet switching network. You've noticed that I've begun to arrange these in an order, but generally all of these fit in the general category of remote computer networks. By remote, let me use some round numbers here. The separation among the computers in these computer networks is on the order of 10 kilometers or greater. That is, these computers are remote from one another. And the speed of communication among them is generally less than 1/10 of a megabit per second. In fact, generally at 10 kilobits per second. Now, historically, in order of historical development, another area of distributed computing, that is the connection of computers to work on a common set of problems, this other area, which may be familiar to you, is that of multiprocessing. Here we have multiple computers connected very tightly, generally in the same room. And here I've shown a list of such multiprocessing computers, perhaps the most centralized of which are things like the ILIAC-4, an array processor, the CDC 6600, the more recent development, the Cray-1, which is now reputed to be the largest computer in the world. C.MMP, the multiprocessor developed at Carnegie Mellon University based on a 16 by 16 crossbar switch of PDP-11s. The Pluribus, a multi-Lockheed Sioux system with, as the name implies, a plurality of buses connecting them. And then the Tandem computer, once again a multiprocessor system very similar to Pluribus. In between remote computer networking and multiprocessing is an area that's only recently developing, an area which I'm calling local networking. It sits between remote computer networking and multiprocessing along this spectrum of distributed computing systems. You'll see here I've tried to indicate that, quite arbitrarily, multiprocessing systems generally have the computers spaced within 1/10 of a kilometer, sometimes even within a meter. And the speeds of the interactions among those computers is at rates in excess of 10 megabits per second. Now, between these sets of parameters is this new area, local networking. That is, the computers in local networks are generally separated by distances between a tenth and 10 kilometers, and they communicate with data rates between 10 and a tenth of a megabit per second. Ethernet is one example of that. The experimental Ethernet that I'll describe in more detail later on is a network for connecting computers within 1 kilometer at a data rate of 3 megabits per second. Other networks which fit in the general category of local networks are, for example, the Distributed Computing System ring at the University of California at Irvine, which has a connection of mini computers joined by a 2 megabit per second ring of twisted pair, so that data is put on the ring and circulates around until it receives it's received by its destination, continues around the ring to its source where it's removed from the ring. Another example of a local network is the Bell Telephone Laboratories Spider Network, which is a local computer communications network connected by in a hub polling system with a centralized communications controller. Yet another is the Mitrix system at MITRE Corporation in Bedford, Massachusetts. This is a computer network in which coaxial cable carrying video is used also to carry data among locally distributed mini-computers. In summary, what this slide attempts to show you is that all these systems, and there are more and more of them with each passing day, have in them a plurality of computers and a communication medium between them. This slide attempts to organize, perhaps unsuccessfully, the set of those systems so that you can begin to understand their relationship. Here I've proposed that the metric for this spectrum is either the data rate of their communication or the distance of separation. Lurking in this idea is the conjecture that there is in fact a conservation law of some kind in operation along this spectrum. That is, the product of separation and data rate is constant along this spectrum. There's a lot of evidence to suggest that this conjecture is false. At the time that the paper was written in 1976, it seemed that most of the systems on the spectrum had a data rate separation product of about 1 gigabit meter per second, or 1 gigabump as we have termed it. What I'm going to be describing is the Ethernet, which sits between remote computer networks and multiprocessing, and as a result has the motivations and characteristics of both. I mentioned that a distributed computer system has computers in it. This is one of the computers for which the Ethernet was developed. The only evidence in this slide of a computer are these two lights located here under this table, which are in fact the power and ready lights of a small Diablo Model 31 disk, which is sitting on top of a cabinet obscured in the darkness here, which contains the computer called an Alto. There are some 200 of these Altos in the Xerox Research Center, which are connected by the Ethernet. Also associated with this computer are its display and keyboard, and what you can see going up the wall here is a cable associated with the Ethernet, which puts this computer in communication with the others in a building. So the Ethernet is a local network, and let me say a few words about how it relates to these other subjects. Remote networking began with the objective of connecting many, many terminals to a centralized computer. Later, through the development of packet switching, through efforts like the ARPA computer network in the early 70s, computer resource sharing has emerged, and this is the use of computer networks to allow the computing resources at various facilities to be shared. For example, sharing the abundance of cycles of computing cycles that might be available at the Iliac 4 site. The purpose of remote networking is to share in an economic way scarce computing resources in general. Now, for multiprocessing, there were an entirely different set of motives. One was that the builders of multiprocessors had discovered that they could not get enough throughput out of one computer, and they hoped by arraying more than one computer on their problems to get much more throughput. And the only problems that had much hope were those which exhibited parallelism. That is, the problem itself could be decomposed into pieces which could be computed in parallel, and the idea would be that you'd assign a piece of this problem to individual processors, and by having them communicate, have them organized so as to solve the larger problem. Another, and this is even more recent than the throughput motivation, another motivation for multiprocessing is reliability. The idea here being if you apply more than one processor to a problem, if one of the computers breaks, you can bring in yet another to continue the job. Examples here would be reliability required for airline reservation systems or process control. Local networks have both motivations. That is, as you will see in subsequent slides, the Ethernet allows computer resources to be shared within a building. Also, it supports algorithms, it supports applications which require the use of more than one computer in order to get them done in time. And then there's the reliability derived by having your computing resources spread around a building instead of keeping them in one lump. Now this is a phrase you probably haven't heard before. For the purpose of this talk, let's use it, calling it incremental centralization. If we imagine a building full of some large number, say 200 or 300 of these altos, there might be some reasons, and I will enumerate them and show them to you, for providing some resources which are best provided by being centralized. That is, centralization of printing facilities, backup facilities, shared files, special computing resources, and long-haul communication resources. Here is one of the altos in the building. The only point in including this slide, which is a terrible slide by the way, is to convince you that there are indeed lots of them. And here's a picture of yet another one to convince you. That is, imagine a building, an office building, with an alto or a computer in every office. Now this looks like a similar picture, except there's an important difference. Located up here in the corner is a printing device. This is an impact printer inside of its soundproof box. Everyone needs to have printing, and in principle each one of these personal computers would require a printer. But because we have communication as provided by the Ethernet, this printer can be shared by some small number of individual personal computers. In fact, there are probably 10 or 15 machines which can transmit documents to this printer should they need to be printed. Another reason for not wanting to have many of these printers, aside from their cost, is that they're noisy, as indicated by this soundproofing box, which attempts to make it less ugly in the office. One often expects, when seeing a computer, that there is going to be a mag tape associated with it. This expectation is reinforced by science fiction movies. Most of the personal computers in the Xerox Research Center don't have magnetic tapes. In fact, this is the only magnetic tape facility in the whole building. There is an Alto computer running this facility, but this is our utility facility. You'll notice there are 2 disks here for doing disk copies, and there's an array of these mag tapes. These mag tape devices are very expensive, and it would be impractical to think of having one on every one of the personal computers. So they're kept here, and for people who need to use a mag tape, say for backing up their files or for archive, they'd come through the Ethernet to this utility station. The point of this picture is to show you the personal computer and to call your attention to this array of disks. You'll notice that this particular user has, yes, there are 4 disks showing here, meaning that his files require more than just 4 disks. In fact, the Ethernet allows a user of a personal computer to have a much larger database and can be practically stored on these small removable disk cartridges. In fact, the user, and this is a picture of a disk system in fairly early state of development. Here we're using larger and less expensive disks for a shared file resource. Larger, for example, than this is an example of the smaller disk that's found on each Alto. Users would want to store files on this larger disk through the Ethernet for 2 reasons. One, as I said earlier, these disks are cheaper by the bit because of returns to scale in the manufacturing of disks. And second of all, there are many files which need to be used by more than one person. So a shared facility like this would be used to hold either files not accessed frequently enough to justify the expense of keeping them on the local disk, or files which need to be accessed frequently by more than one person. This is yet a larger still disk system used to store all the files for everyone in the 200 or so people involved in computing here in the Research Center. There are yet higher levels of incremental centralization. Say, for example, a trillion-bit store associated with the ILIAC-4 could be communicated with through the Ethernet and in turn through some long-haul communication facilities that I'll describe in a moment. This is the Xerox Research Center's version of a data processor. It's in fact a somewhat large time-sharing system. This particular computer is especially good at executing Lisp programs. The idea of personal computers is that most of a user's computing needs can be satisfied by his personal computer. Some applications and some people require access to computing resources larger than that provided by a personal computer. This is a good example. Rather than give each one of these people their own large special purpose computing resource, or rather than having them communicate with such a resource through very special purpose communication facilities, we have put this centralized computing resource on the Ethernet so that it can be accessed from any one of the Altos. In fact, any of the Altos can be, by running the appropriate program in the Alto, converted into a terminal onto this time-sharing system. Here's yet another application of Ethernet which shows it to be somewhat related to multiprocessing. This is a room full of Data General Nova 800s configured into a multiprocessor time-sharing system. Basically a multiprocessor version of this large box, which is a time-sharing system built with one processor. Here, the Nova 800s are connected by Ethernets. You'll notice there are some boxes hung along some cable up here. As you'll see in subsequent slides, these are in fact Ethernet transceivers which provide a communication system, once again 3 megabit per second communication system among these Nova 800s. I spoke earlier about access to specialized resources. This is one of the more specialized. It happens to be an organ keyboard. There is some interest in music composition and generation by computer, but rather than give every personal computer in the building its own very special purpose and expensive keyboard, all these Altos have access through the Ethernet to this particular Alto, which has been specialized with this music keyboard. I mentioned long-haul facilities earlier. This is an Alto, an incrementally centralized server on the Ethernet, whose purpose is to answer telephones. There's a bank of modems here underneath into which users from their home dial with a computer terminal. The Alto then answers the telephone, controlling the modem in question, and then puts this terminal onto the Ethernet so that it can connect with any of the computers on the Ethernet. There are other forms of long-haul communication required, however, aside from that of simple terminals. This happens to be a packet switch on the ARPA computer network, a remote computer network which connects large computing facilities around the United States and Europe and in the Hawaiian Islands. Through the Ethernet, all of our Altos have access to this packet switch on the ARPANET and thereby have shared access to this long-haul communications facility. What I've done so far is explain the Ethernet as a local network and try to give you some of the motivations for why we built it. That is, it is to provide resource-sharing communication and multiprocessing communication among a large number of personal computers located in a single building or in a set of buildings which are near one another. Now what I'm going to do is describe how we arrived at the design for the Ethernet. And to do so, I need to begin with the Aloha computer network. The Aloha Network, as this slide indicates, was the conceptual starting point for the Ethernet. And the Aloha Network, contrary to the Ethernet, was a packet radio network. That is a network using, it happens to be a remote computer networking, using radio transmission facilities to connect a 360 in the Manoa Valley on Oahu in the Hawaiian Islands with a number of computer terminals spread around the Hawaiian Islands and ships at sea. The idea here was that because these terminals would be remotely distributed through the islands and on moving ships, it would be difficult to run cable between them and the 360. This is a 360-65. What I'll be describing, incidentally, is the classical Aloha network as described in Norm Abramson's paper in the Fall Joint Computer Conference in 1970. I would like to indicate the Aloha network has been evolved since that time, but I'll begin by describing the starting point Aloha network in Norm's paper. The Aloha network can be characterized as a radio star. That is, all of these terminals are communicating with a central point, which is in fact a radio packet switch termed the menehune. Menehune is the Hawaiian word for imp, and it's a play on words from the ARPANET imp, which is a packet switch in the ARPANET. I call it a radio star in that it is a radio transmission medium, and it is a star in the sense that all these terminals do not communicate with one another. All of them communicate with directly with the menehune. There are two channels in the Aloha network, two radio channels. There's a broadcast radio channel out of which data transmissions emanate to all the terminals. That is, data packets are transmitted on the outgoing broadcast channel for reception by all of the terminals. The thing which a terminal uses to decide that the packet is for it is that each of these data packets contains an address in its front. So in short, packets going from the jobs running on the 360 through the menehune are broadcast into the outgoing broadcast channel with an address designating which of the terminals to which they're directed. The second channel is an incoming channel, one radio channel called the multi-access channel. It is a radio channel into which all of the terminals transmit multiple access to the same incoming channel. This is the more interesting of the two, more interesting and complex of the two channels, in that one needs to share access to this channel by these terminals. And in fact, it's the method of management of multiplexing of this incoming multi-access channel that characterizes the Aloha network and gave rise to the Ethernet. All of the packets transmitted in this system, both outgoing in the broadcast channel and incoming on the multi-access channel, have a cyclic redundancy check computed for them so that errors can be detected. Errors of two forms: errors due to random noise in the atmosphere, which might cause radio transmissions to be interfered with, and also errors caused by, for example, the transmission at the same time into the multi-access channel of two terminals, sometimes known as a collision. If two terminals choose to send a packet into the central computer at the same time, those transmissions interfere with one another in the multi-access channel, and errors are thereby detected in the menehune. The general method of operation of the multi-access channel is that each of these terminals generates packets that it needs to transmit to the 360. Incidentally, these packets usually contained a line of input to be submitted to the time-sharing system. When a terminal collects such a packet, it simply turns around and transmits it into the multi-access channel toward the 360. It then waits to receive an acknowledgement of correct receipt of that packet by listening to the outgoing broadcast channel, which shortly thereafter it should find an acknowledgement that says, yes, the menehune has received the incoming transmission. For several reasons, it might happen that the positive acknowledgement may not be received in the broadcast channel. The most important of those is that two terminals have chosen to transmit a packet at the same time, and thereby those transmissions have interfered. That is, a collision has happened. And what needs to happen now is that these terminals must retransmit their packets in toward the menehune. Of course, if these two terminals or three terminals or however many participated in the collision simply retransmitted, you can see how these collisions would happen over and over again, each time the failure of a positive acknowledgement triggering a retransmission, triggering yet another collision. So what's done to avoid repeated collision is that these terminals, before retransmitting their packet inward on the inbound channel, generate a random number and wait a random amount of time according to that number. This is termed random retransmission. That is, they do the equivalent of rolling a die to decide how long to wait. By randomizing their retransmissions, I hope you can see that repeated collisions will thereby be avoided, because these, the retransmissions will be scheduled at different points in the future. Another thing to say about the Aloha network is that since it's a radio star, as I said earlier, all transmissions are either from a terminal to the Menehune or from a Menehune to a terminal. As a result, the packets in the Aloha network are one address packets, in that incoming transmissions, the packet contains the address of the source terminal, and on outgoing transmissions, the packets contain the address of the destination terminal. This is another feature of the Aloha net which distinguishes it from Ethernet. The Ethernet certainly began with the Aloha net as the germ of an idea, but in fact there are many differences between the Ethernet and the Aloha net that I'll now go through. The first of these is that the purpose of the Ethernet was to provide communication among computers in a single building. So, for example, we wanted very high data rates and reliable transmission down corridors and through elevator shafts and past typewriters. So it was decided that radio would not be appropriate, especially based on the cost of radio transmission equipment. The Ethernet solves a local communication problem rather than a remote, so radio is not the medium. A second difference is that Ethernet is not based on a Menehune. There is no central packet switching computer to and from which all packets go. Rather, all the personal computers on an Ethernet participate in distributed control of the network. That is, the problem of scheduling transmissions on the network and removing packets from the Ethernet are done in cooperation, in a cooperation among the personal computers which are communicating. A third difference is that there is only one channel in the Ethernet, not two. You recall that in the Aloha network I said that there was an outgoing broadcast channel from the Menehune to all the terminals and an incoming multi-access channel. The Ethernet's channel, its one channel, which we incidentally call the ether, is both broadcast and multi-access. That is, packets which are transmitted into the ether, into the coaxial cable, which is the ether, are transmitted everywhere. That is, they're broadcast to all the communicating stations. And it's a multi-access channel in that any of the communicating stations can broadcast into it. Yet another difference between the Ethernet and the Aloha net is that there is what we call carrier detection in the Ethernet. By carrier detection, we mean the following simple mechanism. Before transmitting its packet into the ether, a station will first listen to see whether there's already a packet going by. That is, it turns on its receiver and listens for evidence of a passing communication. If it finds a passing communication, it simply delays transmission until the presence of the carrier of the passing packet goes away. Carrier, by the way, is a radio term that we've borrowed. Packets, in a packet transmission through a radio system, there would be a carrier indicating that the radio transmitter is on. In the Ethernet, we detect the passing of a packet by detecting its, quote, carrier. By having carrier detection, a lot of collisions are avoided. That is, when an Ethernet station detects that there's a packet going by, it doesn't transmit and thereby collide with that packet. Another difference between the Ethernet and the Aloha network is collision detection. This is a process by which an Ethernet station, while it's transmitting a packet, examines the content of the cable, listens to the cable at the same time to discover whether there's a discrepancy between what it's transmitting and what's actually getting onto the cable. If there is an interference, a colliding transmission, it'll cause the cable itself to be scrambled, and the circuitry in the Ethernet transceiver, which I'll show you in a minute, will detect this collision. This is a feature of the Ethernet which would have been very difficult to provide in the Aloha network, in that radio devices, in a radio system, the receiver is very often saturated by the transmitter. In the case of electrically driving a coaxial cable, it is possible to listen to the cable and detect whether there is interference. Another difference between the Ethernet and the Aloha network has to do with retransmission control. In Norm Abramson's Fall Joint Computer Conference paper in 1970, he gives us some analysis which shows that after a while, the Aloha channel into which terminals are injecting packets. If you add enough terminals, or if each of the terminals generates packets at a fast enough rate, then the channel soon becomes garbled and full of retransmissions occurring and reoccurring. As a result of a lot of analysis, it's been shown that there are methods of controlling the retransmission process so that the channel doesn't become unstable if the traffic load gets too heavy. We'll be coming back to this both later in this particular tape and in detail in the Ethernet Part 2 tape. Another, and this is a detailed difference between the Ethernet and the Aloha network. I mentioned earlier that Aloha network packets have one address, in that all packet transmissions are either to or from the Menehune. There is no Menehune in the Ethernet, and so every packet originates from one of the communicating stations and is addressed to another of the communicating stations, so that to correctly identify the source and destination of a packet, one requires two address packets. This is at last a picture of the Ethernet, and let me run through it slowly. This heavy green line is the ether itself, which in our Ethernet is a 0.406-inch coaxial cable, RG11 style foam cable, for those of you who know about such things. This coaxial cable is terminated in two places at each of its ends. A station wishing to transmit injects its packet into the cable, and the packet propagates through the whole cable, finally burning itself up in the terminators at the end. The pieces of the Ethernet are the tap. The Ethernet tap is a device for physically grabbing hold of the coaxial cable and puncturing it so as to establish electrical connection between the center conductor of the coax and the transceiver electronics inside the transceiver itself. The transceiver and tap are part of the same assembly, and I'll show you a picture in a moment, are generally located in the ceiling or under the floor sometimes, right next to the coaxial cable. And then between the transceiver and the communicating station, and this is the personal computer, is an interface cable, a bit serial cable, which in the case of our experimental Ethernet has 5 signals on it, two flavors of power, serial data out, serial data in, and then yet another signal which indicates that a collision is being detected by the transceiver. And now inside the station is an interface, piece of hardware for generating serial bit streams. Its basic function is serialization and deserialization of data, and the controller, whose general function is scheduling the transmission of packets from various processes in the station, and also controlling the retransmission process, as I alluded to in the previous slide, controlling it so that the sharing of this cable is always at the optimum. To remind you, here once again is a picture of an Ethernet station, an alto. Once again, the two colored lights indicating that its disk is on. And you'll note some more disk cartridges here. And here is the gray interface cable. In this picture it's shown beneath a false floor, but in fact most of our transceivers are in the ceiling. Imagine this gray cable going between the alto, between the Ethernet station and the transceiver. Here's the transceiver itself, which you can see compared to this 1-foot ruler. It's a metal box containing a small amount of mainly analog circuitry. This shiny block here is in fact the tap. The tap consists of two pieces, the tap block, which is what you can see here, which you bolt to the cable, and then there's a separate assembly called the stinger. The stinger is part of the transceiver, and you screw it into the tap block, and the stinger then punctures the coaxial cable, as I mentioned before. Okay, there are two other things to say about this picture. One is the simple method for installation, and the second is the advantages of this method over others. The way one installs an Ethernet is the coaxial cable is run generally down the center of corridors in a building. There isn't one anticipated for each communicating station. One just simply tries to route the cable so that it gets within within 40 feet or so of every possible place that you might want to put a communicating computer. When it becomes time to install one of these personal computers, one of these Ethernet stations, you then route this gray cable up from it into the ceiling, right up to the coax. The first step is to bolt the tap block onto the coaxial cable. And having done that, there are two little needles in the tap block which puncture the outer casing and grab hold of the shield. Then you insert a drill which goes into a threaded hole, a part of the tap block, and you tighten the drill down. And what this drill does is it cuts away the casing and the outer shield and gets you right to the foam of the cable. Then you remove the drill, and I'll add a few more details. You also need an X-Acto knife and a brush to clear away the debris left behind by the drill. And then having done that, you then screw the transceiver into the very same hole that you just took the drill out of. And what you're screwing in now instead of a drill is a needle-like device which goes all the way through the foam and sticks into the copper center conductor of the coaxial cable. Now there are a couple of advantages for connecting to an Ethernet in this way. One is the Ethernet doesn't have to be brought down every time you want to install or remove a communicating computer. All you have to do is walk up and tap, and we have no evidence that a packet has ever been lost in this particular way. Another advantage is the reliability. The power for this transceiver is provided through the interface cable by the station. That station can be powered up and down. The transceiver can be powered up and down. Power is not required in this transceiver to allow signals to pass through the coaxial cable, which in fact has not been interrupted. As a communication system, you can see that the only shared portion of this system, the only one which is in common to all the communicating stations, is this passive, unpowered, black coaxial cable lying in the ceiling. Because it is powered and unpowered and passive, we've designed it with the expectation that it would be highly reliable. This, for example, could be contrasted with the distributed computing system ring. To build a ring, it is necessary to cut the cable at each ring interface and to insert a box which regenerates the bits from one side to the other. This means that you need to bring the network down when you're installing a new station, and it also has some reliability implications in that the repeating ring interface needs to be continuously powered during ring operation. Let me allow you to look at this slide for a moment before telling you that this is not a picture of an Ethernet. There's not one of those cables is an Ethernet cable. What this slide intends to do is show you a problem, and this has to do with the connectivity of a network, or how you choose to decide on the topology of a network. There's a technical term which describes this sort of room, and there are many buildings across the United States which have rooms that look like this. The technical term for such a room is it's called a rat's nest of cables, in that all these cables from all the communicating devices, and sometimes they're telephones and sometimes they're personal computers, just like the ones we've shown you, when they all come together, you have this very complicated, messy area. In designing the Ethernet, we attacked this problem head-on. We considered a number of alternate topologies for use in the Ethernet, and what I will attempt to do now is to go through these four alternatives to the Ether and give you the rationale for why we decided against them. It's not my intention to make this discussion totally convincing, just to give you the rationale. We could have decided to connect every one of the personal computers to those others which it needed to communicate with. However, in designing the Ethernet, we came in with the assumption, which has turned out to be quite correct, that every one of these personal computers has frequent occasion to communicate with a large number of others, in fact, very often almost all of them. The result of that would be that connecting communicating stations on a point-to-point basis would result in their being fully connected, in that every station would have to be connected to every other. Now, we were planning on having several hundred of these communicating computers in a single building, so you could see how very quickly all the cables necessary to provide all the connectivity that was required by the distributed computing system we're trying to build here would lead to a growing combinatorial menace, a rat's nest of cables. So we decided against ad hoc point-by-point connection. because we felt it would lead inevitably to a nearly fully connected network and to a large number of cables. Another alternative would be to connect all of the communicating computers to one point, a so-called star network or hub-connected network. Here, each of the communicating computers would talk to a central communicating facility. It so happens that the previous slide was a picture of one such star network that we had here at the Palo Alto Research Center before building Ethernet. There are several problems with this approach. One of them is that the centralized communication switching node needs to have a communications capacity which is large enough to handle the aggregate of communication demands of all of the communicating stations. Second of all, it's a point of single failure in that if the communication node breaks, then communication is lost among all of these stations. Another somewhat more subtle reason for not liking this hub-connected or star approach is that we had envisioned that we'd like to be able to build our distributed computing systems starting small and then allowing them to grow, or perhaps to build a number of them, some small and some large. If we depended on having a centralized switching node, this central node would have to have the capacity to handle the large networks and still handle the small ones. Such an architectural approach would tend to make the small systems uneconomical. For example, if you had only 2 communicating stations, you couldn't put them in communication until you had bought this separate communications box, which would have much more capacity than that required for communication between 2 machines. Another alternative, and this is called store and forward packet switching or store and forward routing, is one that we pursued as a result of our familiarity with the ARPA computer network. This is a system in which packets are given to a subnet of store and forward packet switches which do alternate routing and direct and delivery of packets to the communicating stations. In this picture, the communicating stations are designated with round dots and the packet switches with black dots. We in fact followed this alternative quite far before abandoning it. It turns out just to be overkill for the problem we're trying to solve. One thing we observed is that the expense of such packet switches is comparable to the expense of the personal computers that we wanted to put in communication. Yet another alternative, and this one came very close to satisfying our needs, is the loop or ring, as we have now come to call it, in which the personal computers would join through their ring interface to a ring of circulating packets. And in order for a transmission to happen, one of these personal computers would put its packet on the ring. The packet would circulate around the ring to the destination and then proceed past the destination back to the source where it would be removed from the ring. And as I've already mentioned several times previously, this method was not desirable because it involves breaking of the ring for installation, thereby bringing the ring down. It also requires that all the ring interfaces be continuously powered so that they can regenerate signals at each point. So this is a reliability problem in that the probability of failure multiplies with the number of stations on the ring, and at each point you're injecting not a passive tap which leans up against a coaxial cable, but rather with an continuously powered and actively repeating ring interface. So finally we came to this last alternative, the so-called ether topology, which is in principle an unrooted tree with no intelligence whatsoever, simply a medium through which packets can be transmitted. There is no central control required in that the ether itself is simply a medium which carries a transmitted packet to all places. There is no switching in the ether itself. For you mathematicians, you can see how the ether is the dual of a star network. In a star network, you have distributed interconnection in that each of the communicating stations has its own communications path, and you have centralized switching. That is the centralized switching hub or node. That is distributed interconnection and centralized switching. In the ether, you have simply the reverse. That is, the interconnection is centralized. That's provided by the coaxial cable which forms the ether. And the switching of packets is distributed among the stations. As I've shown it here, the ether can branch in principle. In fact, it's in principle possible to build an ether which branches passively using non-powered passive circuits to do branching of the coax. In the experimental Ethernet upon which this talk is based, we have built our transceivers with a power and sensitivity such that they don't permit passive branching. To go through a passive branch, one suffers an attenuation. We've been able to achieve dimensions of our network without doing passive branching. This is in fact a picture of a several-year-old picture of the Ethernet on the second floor of the Xerox Palo Alto Research Center. The red line indicating this coaxial cable, which, as you may be able to see, wanders down the center of our corridors here. There's this particular busy room in which the cable goes once around the room, and that happens to be the room that I showed you earlier with all those 10 or 15 Nova 800s. And then it wanders through the remainder of the corridor. Each of these little circles is an Alto, a personal computer, and then these little lines connecting the circles to the coax are the interface cables going up to the transceivers, which are in the ceilings along this coaxial cable. In fact, at this point, the cable makes a transition from being in the ceiling through this whole part of the building to going into the false floor, which the computer science laboratory is fortunate to have. At this point, the cable actually goes down through a telephone conduit to a lower floor where it's connected up with the Ethernets on the lower and upper floors of the research center. The Ethernet is a distributed packet switching system. In fact, the title of the Communications of the ACM article that I mentioned earlier is Ethernet, Distributed Packet Switching for Local Computer Networks. Some explanation is required for this, in that many experts in the field claim that the Ethernet isn't packet switching, and I'll just explain to you the sense in which it is. First, let me summarize the algorithm whereby packets are put on the cable. It turns out the Ethernet is distributed packet switching in two senses. One, the way in which it puts packets on the cable, and the other is the sense in which is the method used for removing packets from the cable. If you look here, here's a picture, a timeline of the passage of time on the cable. Packets are preceded by a short period of quiet. There's a synchronization phase, which on the current experimental Ethernet has 1 bit of synchronization. There's 8 bits indicating the destination address of this packet, followed by 8 bits indicating the source station of this packet. There's then an arbitrary number of 16-bit data words, followed by a 16-bit cyclic redundancy checksum, followed once again by quiet. And as I mentioned earlier, packets are put onto the coax in the following way. Each station which has a packet to transmit waits for quiet. You recall I termed this earlier as carrier detection. They wait until there is the absence of carrier or that the cable is quiet. Each such station then begins to transmit its packet. While it's transmitting, it examines the transmission with its receiver on to detect whether there is any interference in the process of transmission. If there is no interference and the entire packet has been transmitted, the transaction's complete. However, it can happen that during a transmission, interference will be detected. In that case, it's necessary for the station to randomize, as in the Aloha Network, as I explained earlier, to randomize its retransmission so that the collision will not recur repeatedly. So there's a randomization followed by a retransmission. Now, this particular algorithm, which I've summarized in 5 words, is a distributed algorithm which is executed in each of the communicating station and which results in a sharing of this cable. The model that I'll describe in the Ethernet Part 2 videotape will go into detail as to the effectiveness of this multiplexing scheme. So I refer to this as distributed packet switching in the sense that packets are put onto the cable in a manner which is distributed using a distributed algorithm by all the communicating stations. The Ethernet is also distributed packet switching in the sense that routing is accomplished by broadcast address recognition rather than there being a single station or a set of stations which routes packets to their intended destination. The packets are simply broadcast into the cable. Destination addresses are recognized, and then if there should be an address match, the packet as it passes is copied into the main memory of the destination station. There are in fact three conditions under which a packet is copied into a station. One of them is if the destination address of the packet matches the machine address. This is the normal case. That is, I, as a communicating station, wait for packets to go by whose destination address is me. And in such cases, I copy that packet into my memory. There are two other cases under which I will copy a packet in. One is if this packet has been designated a broadcast packet. There are packet communication protocols which rely for performance on their being able to use broadcast. Broadcast packets are indicated by in the case of our experimental Ethernet, by putting a 0 in the destination address. So that if I, as a station, see a packet go by with 0 in its destination address, I identify that as being a packet intended for everyone, and I copy it into my main memory. There's yet a third condition under which packets are copied into main memory, and that's if one of these stations if a station is put in a mode which we call promiscuous. That is, a station is willing to copy all packets regardless of their address into its memory. This is a mode which is very useful for diagnostic and measurement purposes. So in summary, the Ethernet is distributed packet switching, as to be distinguished from store and forward packet switching, in two senses. The putting of packets on is done by randomized contention and retransmission according to a distributed algorithm, and packets are removed by broadcast address recognition. That is, all stations participate in the routing decision. Let me now explain a little about how bits are put on the coaxial cable, and this will lead into a brief description of the performance of the Ethernet, which will be detailed in the subsequent tape. Data is put on the coaxial cable by the transceiver being turned on and off alternately by the station's controller. In each bit cell, we use a method which is used on magnetic tapes and is sometimes called Manchester encoding or phase encoding. In each bit cell, we first transmit the complement of the bit followed by the bit. This guarantees that in the middle of every bit cell there is a transition, either from off to on or from on to off. This allows both the data and the clock to be encoded at once. That is, you see here that the time of the bit transmission is established by the transition, and the value of the bit is established by the sense, whether it's 1 to 0 or 0 to 1. There is, in fact, no global time base in the Ethernet. Each of the transmitting stations encodes data and clock in the transmitted packet, and then the data and clock are recovered by the receiving station. This particular method of transmission is also necessary for useful for carrier detection, in that since in each bit cell there is a guaranteed transition, a station can tell whether there's a transmission within a bit time simply by noticing whether or not there has been a transition in the bit cell. So, for example, a large packet consisting only of zeros will still result in there being periodic transitions, so that one won't get a false indication of absence of carrier. This particular method of transmission is also useful for interference detection. The transceiver, in fact, is a two-state transceiver. It is either on or off. During the on periods, the transceiver is a low impedance, as we electrical engineers say, and it's very difficult. It would be very difficult to detect a collision. However, during its off periods, it's high impedance. That is, it can during such periods detect the presence of somebody else driving the cable. So in fact, the way interference detection is accomplished is during the periods that the transceiver is off, the transmitting portion of the transceiver is off, the receiver looks to see whether in fact the cable is being driven or not. If it's still being driven, that means somebody else is driving it and that an interference is happening. Go. As we reach the end of this tape, let me speed up a little and point you to the subsequent tape, which will go into some of these areas in more detail. I've just finished showing you how we use these self-clocking packets to allow interference detection. We detect these interferences at the source of a packet, so that, for example, we can immediately reschedule retransmissions so that we can keep garbage transmissions short by aborting them almost immediately. And we can also use them as a traffic indication. And I'll be elaborating on this point in the Ethernet Part 2. The efficiency of an Ethernet, and I will go through a mathematical model in the next tape, it can basically be measured in terms of the ratio of packet duration to end-to-end propagation time. And for the parameters of the experimental Ethernet, that is 1 kilometer, 3 megabits per second, using 4,000-bit packets, it turns out that the efficiency is well up almost to 100%, certainly above 95%. In the next tape, I'll be describing the stability of the Ethernet channel as opposed to that of the Aloha channel. In building an Ethernet, eventually some of its parameters are violated. For example, after concatenating a sufficient number of cables, it can so happen that the cables get so long that the power and sensitivity of the transceivers is violated. In such cases, we can regenerate the signal by putting in a packet repeater. That is a device which regenerates the electrical signals, restoring them to their to a sufficient strength to be received at great distance. The only trouble with putting a packet repeater in the network is that, in fact, you now have an active powered component in the shared communication facility. You can then concatenate cables and use repeaters to regenerate signals, but eventually you'll have too much traffic in the cable so that the communicating stations are not getting sufficient access to the cable. This can be accomplished by building more than one Ethernet and putting traffic filters between them. A third way in which an Ethernet can be overgrown is by attempting to put more than 256 stations on a single Ethernet. There are only 8 bits of address in an Ethernet. This problem is accomplished by using gateways, that is, devices which extend the address facilities of the Ethernet through software interpretation of addresses carried in Ethernet packets. This is extension of the address up, so you can address more than one Ethernet, and down, so that you can address multiple points within a single station. Here is a picture of 3 repeaters growing an Ethernet, and you can see that this is the most complex part of a communication system supporting over between 200 and 300 altos in 3 different buildings. And this is a picture of a packet switching gateway which connects 3 Ethernets and keeps their traffic isolated one within the other and does extended address interpretation. Now, given an Ethernet, is it error-free? And the answer is no. In an Ethernet, packets are delivered only with high probability, and as a result, packet protocols are required. In the next tape, I will go into an example protocol which is introduced in the Ethernet paper. So thus far, I've discussed the Ethernet as a local computer networking connecting up to 256 stations through up to 1 kilometer of repeaterless cable at 3 megabits per second. I've described to you the 2 senses in which the Ethernet is distributed packet switching. That is, it uses randomized contention to get packets on the cable and broadcast address recognition to get them off. The third point to be made is that the Ethernet requires packet protocols to provide reliable transmission. I now invite you to see the next tape, Ethernet Part 2. Welcome to videotape entitled Ethernet Part 2. I assume that you have already seen the videotape entitled Ethernet Part 1. In this second hour, we'll be focusing on 2 subjects, performance and protocol, and going into detail. Details which, incidentally, are presented in the original and only Ethernet paper published to the Communications of the ACM, July 1976, by myself, Bob Metcalfe, and my colleague David Boggs. Other useful background, especially in both areas of performance and protocol, will be found in a report entitled Packet Communication by myself, Bob Metcalfe, published by MIT Project Mac. Its technical report 114, published in December 1973. In the earlier discussion, I've already touched on both of these subjects. One is I pointed to the difference between the Ethernet and the Aloha Network by saying that there were some performance differences, in particular the stability of the Ethernet. There are stability mechanisms in the Ethernet not provided by the Aloha Network. And I also mentioned that once you had an Ethernet network, that it wasn't sufficient for providing reliable communication. That is, packet protocols are required. This talk will have two halves. I'll go through a mathematical model of performance, and then I will describe a very simple packet, so-called packet protocol, and describe it briefly and give some of its strengths and weaknesses. The Aloha Network, in fact, it was a reading of the Aloha Network paper that first got me interested in the Aloha Network because of the deficiencies of its mathematical model. The details of communication hadn't quite interested me at that time. It turns out that an Aloha Network, and recall I showed you that diagram earlier of these terminals transmitting into this menehune through a multi-access radio channel. And in the Aloha Network, the efficiency of the incoming channel is 18%, the maximum theoretical efficiency, meaning that if you add enough terminals and enough traffic, in the best of all possible situations, theoretically, according to Norm Abramson's model in his 1970 paper in the Fall Joint Computer Conference, only as much as 18% of this channel can be effectively used by the statistical retransmission, randomized retransmission strategy. For a slightly modified system called a slotted Aloha system, up to 37% utilization of the incoming multi-access channel can be achieved. I should say that for the Ethernet, one can get asymptotically close to 100% utilization in a way that I'll be describing briefly in this model. The analysis for the Aloha Network is captured in the following picture. This curve, which describes the performance of an Aloha channel, has traffic on the horizontal axis and load on the vertical axis. In other words, this is the rate which Abramson designates as S. This is the rate of packets generated by the terminals, for example, the count of carriage returns of users sitting at their terminals. This traffic, which he denotes as G, is the number of packets which are actually carried in the channel. That is, it counts the new packets plus their retransmissions. And the analysis which Abramson performs shows that as the load goes up, the traffic goes up, and suddenly there's this point after which, if you add more load, well, you can't, because suddenly the traffic drops away. That is, there's a certain point in the loading of the Aloha channel, this point, after which adding additional traffic reduces its traffic carrying capability. This is a point of instability, and it works in the following way. The channel is so full of retransmissions and new packets that every time you try to transmit, your packet gets collided, which causes you to add more packets and more retransmissions, so the whole channel collapses in one unstable explosion of packets and retransmissions. This was the so-called Aloha result, which leads to this number 18%, which incidentally is 1 over 2e. And it corresponds to the maximum in this curve here, which is 18%. It was observing that if we were to have an Ethernet channel, we would not want to have this instability. What we'd want is a curve that it looks something like this, that is, became asymptotically close to 100%, and that is, and more particularly, that its performance was monotonic. That is, as you added more and more load, your performance would degrade gradually rather than ending up in an explosion of retransmissions. Now, in the Ethernet, there are some differences, some of which we've been over once before. Let me summarize them. One of them is carrier detection. That is, in the Ethernet, you listen before transmitting. This is a form of a more general principle that we call deference. That is, we've built into the Ethernet the model that if there's ever a conflicting transmission detected, either before the start of transmission or during, it is built in that a transmitting station will defer. As a result of deference, we have a phenomenon called acquisition. Acquisition. That is, since it's built in that stations will defer to other transmissions, that if I as a station have managed to get started transmitting and have been transmitting a packet for long enough, all of the other stations on the coaxial cable will be already hearing my transmission. They won't start their transmissions. As a result, they will let me transmit indefinitely. It can be said that I have acquired the ether. This explains one of the important differences between the Aloha network and the Ethernet, in that in the Aloha network there was no carrier detection and there was no deference, so that even if I had even if I had been transmitting for a long time, somebody else generating a packet would come in and immediately clobber me, so there was no notion of acquisition. It is in fact acquisition which allows us to get up to 100% transmission efficiency simply by making our packets long enough. Another feature is interference detection, another form of deference, in that if you detect interference, you immediately truncate your colliding transmission. This also serves to increase performance, in that once a packet has been collided with, it's immediately terminated. So that on the network, you get very short collision bursts, which are truncated because of the collision detection mechanism. And this adds to efficiency. So if we look at the network, at time now on the Ethernet, this is the tail end of a packet transmission, and then there'll be a series of collision bursts according to the collision detection and retransmission, and then it'll be followed eventually, and remember there's randomization going on here, after a series of these trial collisions and retransmissions, finally one of the stations will decide to transmit, will begin transmitting, and having begun, if it just gets started and everyone else is deferring, then it can run to completion. That is, it can transmit an arbitrarily long packet because all the other stations will defer. So we call this the acquisition interval. We call this the contention interval. And so time on the Ethernet cable is divided between contention intervals and acquisition intervals. Now, the Ethernet model, which I'm now going to describe, is a very simple one. It's presented in the CACM paper, July 76. It gives one a rule of thumb of Ethernet performance. It shows how Ethernet efficiency can be asymptotically close to 1. And not only that, at the same time, it gives you an idea about the operation of the Ethernet on its cable. The parameters, there aren't many parameters to this model. There are 4. There's P, which is the packet length. That is the number of bits per packet. There's C, the capacity in bits per second of the coax. And by the way, this is 3 megabits per second in our experimental Ethernet. And then there's T. Now T is the duration of a slot time. And let me show you that each one of these collisions, and by the way, they don't all have to be collisions. Some of them can just be silences. Each of these is a retransmission slot. Now, the duration of a slot is the amount of time that it takes for a transmission to be initiated and for the transceiver to detect a collision if there is one. And it turns out that the amount of time that you have to wait to detect a collision has to do with the time it takes for your transmission to get all the way to the far reaches of the coaxial cable and then to come back. That is, a slot time is on the order of the time for an end-to-end propagation time from one end of the network to the other. And finally, there's Q. And Q is the number of transmitting stations queued. And in our simple model, we contend that there are a fixed number of such stations, that the number of them has to be large for the model to be accurate, and that they're all contending for access to the cable. So another thing I've just told you is that this model is appropriate in the heavily loaded case. That is, there are constantly Q stations queued for transmission. So in each slot here, there are Q stations who would like to begin transmitting. And what they do is they transmit to us. Each of them, according to this model, will attempt to begin one of its transmissions in a slot with an exmission probability x, which we presume to be the same for all these competing stations. It turns out that the optimal value for x is 1 over q. That is, if there are Q stations contending for access to the cable, if they're all to have an attempt probability, a transmission probability, a probability of attempting a transmission in one of these slots, the optimal number for them to use is 1 over the number of such stations, that is 1 over Q. Now this is one of the assumptions in the model, and for example, this is a somewhat unrealistic assumption in that it assumes that each of the stations is aware of how many stations are competing with it. You have to take this as an act of faith and assume that it's one of the points of inaccuracy of the model. In fact, in the real Ethernet, stations do in fact perform a procedure to try to keep an estimate of Q so that they can approach the optimal retransmission rule. Now in trying to analyze now the fraction of time that the network spends successfully transmitting packets, that is the fraction of time it spends in acquisition intervals, versus the fraction of time it spends in contention intervals, the first quantity of interest is A, which is the probability that one and only one station will begin transmission in a given slot. Now, if there are, that's the probability that one station chooses to transmit and that the remaining Q minus 1 stations decide not to transmit. And since there are Q stations, there are Q ways in which that can happen. But we're now assuming that x equals 1 over Q, so it turns out that A is given by this simple formula. That is, the acquisition probability, the probability that, given that there are Q stations attempting to transmit, the probability that only one of them will transmit and therefore result in an acquisition interval. You see, in this slot here, which is the beginning of this acquisition interval, one station decided to transmit and all the others decided to defer. And as a result of that, this station acquired the network. This is the formula for the probability of an acquisition interval beginning. Now, the next quantity of interest is W. That is the number of slots that you will have to wait, wait, before an acquisition interval begins. Well, you'll have to wait 0 intervals with probability A. That is, in the very first slot with probability A, one station will begin transmission and all the others will defer, so therefore with probability A, the number of slots that you'll be wasting in the contention interval is 0. And you'll have to wait 1 with probability A times 1 minus A, and you'll have to wait for 2 slots with probability A and 1 minus A squared. That is, this is the probability that there was an acquisition, there were 2 failures to acquire, and so on. All the way to infinity, there is some finite probability that you'll never acquire the ether, that you'll have to wait indefinitely. And what we have here is a geometric distribution, which if you sum in a straightforward way, you get that the number of slots that you'll need to wait before acquiring the ether is given by 1 minus A over A. Now let's perform a few intuitive checks on these 2 results we have thus far. If Q equals 1, and you substitute in there, you get that A equals 1. As Q equals 1, that's 1 over 1, that's 0 to the 0, and we all know that 0 to the 0 equals 1. So that means that if there were only one station, the probability of acquisition in one slot would be 1. And of course that's true. If there's only one station contending, his exmission probability x will be 1, and therefore acquisition will happen with certainty. So that's certainly a reasonable result. As Q goes to infinity, that is if there are a lot of competing stations, it so happens that A goes to 1 over E. This is the familiar this comes from limiting. If you take the limiting case of A as Q goes to infinity, you get A approaches 1 over E, and this should be familiar to you from the Aloha result, which is true for the infinite population case. And I'm sorry, I don't have time to go into detail on Abramson's model. Now, if we look at W here, if A equals 1, you plug in 1 there, you get 0 over 1, you get W equals 0. Well, that makes sense too, that if the probability of acquisition is 1, that is certainty, you'll have to wait no time. And another intuitive result is if A equals 0, then W goes to infinity, which is also a satisfying intuitive result. That is, if the acquisition probability is 0, you'll have to wait forever. Okay, now with these two intermediate results, that is A, the probability of an acquisition, and W, the number of times to the number of slots that one will have to wait on the average to acquire, we'll now look at, do it over here, we'll now be able to get directly to the efficiency of the Ethernet. Now, the efficiency would be given by the ratio of the time spent sending successful packets, that is time spent in the acquisition interval, divided by the total time. So the time spent transmitting a packet is given by the duration of the packet, that is the number of bits in the packet divided by the rate at which they're transmitted. So this is the amount of time spent transmitting one packet. But every time you do that, the total time you spend is given by this formula. That is, we're looking for the fraction of the time, and let's take this as a recurring period in the operation of the Ethernet. We want the fraction of the time spent transmitting a packet. Well, that's this, P over C, divided by the whole interval, which is P over C again, plus the length of the contention interval. But we've just calculated the length of the contention interval. That's the number of slots that we'll have to wait before we acquire the ether. And each one of those slots has duration T, that is the number of seconds in a slot. So this is the efficiency. In the Ethernet paper, we've evaluated this formula for efficiency. And in the case of the Ethernet, we used a number of different packet sizes from 48 bits through 4,000 bits. The capacity is 3 megabits per second. And W here, it turns out for W that, let me see, it turns out that as Q, as I've indicated here, as Q goes to infinity, A goes to 1 over E, and W goes to E minus 1. That is, as A goes to 1 over E, W goes to E minus 1, which is approximately equal to 1.7. So that for a loaded system with more than 10 users or so, this is effectively 1.7. It's very simple to evaluate this efficiency for varying packet sizes and capacities, and we've done so in a table in the Ethernet paper. Let me give you a few representative numbers. If you were to have 256 communicating stations in the Ethernet, that is a queue of 256, and they were to be using a packet size of 4,000 bits, which incidentally is a very common packet size. We use it as our maximum packet size. That gives you an efficiency of according to the formula which I just ran by you quickly and which you'll find in the paper, an efficiency of 98%. Looking at the other end of the spectrum here, if we were to use 256 competing stations but only use a packet size of 48 bits, would get an efficiency of 37%. Now this should be a familiar number from what I've said earlier. 37% is the efficiency of a slotted Aloha system. It turns out that this model I've described, it degenerates to that of a slotted Aloha system when the packet duration gets so short as to be equal to a slot time. Then you have slotted Aloha, and this model shows that in that if the packet size becomes short enough to equal one slot time, in this case 16 microseconds. By the way, I mentioned before the slot time has to do with the propagation time from end to end. It's 16 microseconds in the case of a 1 kilometer network based on the propagation of the speed of electrical signals through the coax, roughly the speed of light. And to choose a more intermediate number, say we had only 10 competing stations, and let's say they were using 1,000-bit packets, you get an efficiency of 93%. So you can see that the efficiencies of Ethernet transmission can be quite easily much higher than this is the theoretical maximum efficiency for slotted Aloha, and 18% is the theoretical maximum for regular classical Aloha. It's easy to get much higher than those efficiencies through appropriate choice of packet size. In fact, for the typical case for us is usually in excess of 95% based on the number of competing stations that we have from time to time and the packets that they use. There's a rule of thumb which says that an Ethernet can be efficient as long as the ratio of its packet duration is large relative to the diameter of the network, relative to the end-to-end propagation time. In other words, the ratio of packet duration, P over C, to, and this might as well be T, as long as the end-to-end round-trip time of a piece of coax is small relative to the packet duration time, then an Ethernet will have high efficiencies. So you just look at the ratio P over C, T, or D, changing notation here. As long as this number is large, say about 100, then efficiency will be high. Okay, I've now run through quickly the performance model in the Ethernet paper, shown you why the Ethernet is more efficient than an Aloha channel based largely on carrier detection, which allows packets to allows stations to acquire the ether, and then also interference detection, which allows the collision bursts to be very short. Okay. In this talk now, I think I've finished describing the performance of the Ethernet, in particular trying to contrast it to the Aloha network, and showed that we could get asymptotically close to 100% utilization of the coax through this distributed algorithm, distributed packet switching that we have, which relies on carrier detection and interference detection. You may recall from the previous tape, I pointed out that even though we now had an Ethernet that was able to use the network with some high level efficiency and with some reliability, that is, packets can be delivered only with high probability, leads us to say, well, what good is a communication system that won't deliver packets reliably? And the fact is that the Ethernet is built with the assumption that above it are so-called packet protocols. And what I'm going to do in the remaining half hour or so is describe a very simple packet protocol, one that's described in the paper, Communications of the ACM paper. And this happens to be a protocol that we use for some years with great success. It is not a modern protocol or one that we would recommend that you use. In fact, what I'll do is try to spend a few minutes at the end summarizing the deficiency of this rather simple packet protocol. Let me spend a few minutes defining a couple of words in the packet protocols area. If you read the newspapers these days, you'll find a lot of mention of protocol issues, and let me spend a few minutes talking about protocol in general. Two words that get used a lot in the protocol arena, the word message and the word packet. In fact, in the one must exercise great care in the use of these words because they have different meanings from time to time. In the ARPA computer network, for example, these words have very particular special meanings. Messages happen to be exchanged among hosts, and they have 8,000 bits in them. Packets are exchanged among ARPANET imps, and they have 1,000 bits in them. But that's a very special technical use of these words, and let me attempt to give you more the gist of how they tend to be used. Messages tend to be the higher level constructs. In fact, very often messages are sent among humans. I will send a telegram from point A to point B. A telegram is like a message. It's something which is handleable by a human being, usually contains some human interpretable information. Whereas packets, the word packet tends to be used to describe some data which is sent among computers rather than people. Of course, to send messages among humans, you have to break them down into packets to be sent among computers. It's just that much more computer processing is implied by the use of the word packets. Messages tend to be of variable and unconstrained length. And it's very often in a process called packetizing, it's necessary to break such messages into packets, which are generally have some fixed maximum length. This is a recognition of the fact that packets have to do with the computer technical side of things, and it's very convenient to be able to limit your transmissions to some fixed length. Another parameter which often distinguishes the words message and packet is that messages are generally delivered in minutes and hours, if not days, whereas packets tend to be delivered in milliseconds. In fact, 200 milliseconds is a number for the used for the ARPA network. So look out for these two words, message and packet, and here's an attempt on my part to characterize how they tend generally to be used. So now when I say packet protocols, what I'm describing are protocols among computers who send digital data packets, like the packets sent through the Ethernet. And the purpose of these protocols is to absorb the perils that packets encounter going from point A to point B. The purpose of packet protocols is to get reliable communication of a form useful to, for example, human beings for transmitting messages. So packet protocols have more to do with the exchanges among computers, and I'll be getting into that. And now I have a few more general terms to introduce. And these are a set of, in principle, orthogonal pairs. If we have data flowing through a communication network like the Ethernet, this data generally has a sender and a receiver. And those two terms describe that data is flowing. Data, the end data, the messages, if you will, are flowing from a sender or receiver. But in the course of supporting this flow of data, very often packets have to come back this way. And in such a case, for example, an acknowledgement or a flow control message that says, oh, slow down or speed up, or could you send that one again? Well, such a packet, you can see, is going from the receiver back to the sender. So we have another pair of words to describe the source and destination of a packet. And with these two word pairs, you can see very quickly how you could construct seemingly nonsensical sentences like, this is a packet whose destination is the sender. Now, to set up this data transfer, one of the sides had to initiate the flow. One of the sides, the sender or receiver, had to start the transfer. For example, the sender says, gee, I have some data to send to the receiver, and so he starts by sending it. Another way that could have happened is that the receiver could say, you know, I need some data from the sender, and he initiates the flow in his direction. So we have these other two words which have to do with the initiator and listener. In order for the receiver to decide to initiate a transfer, the sender has to be listening to respond to such requests. So there's the initiator of a transfer as opposed to the listener. That is the passive actor which waits to be probed. And a final pair of words, user and server. If you have two communicating processes in a computer network, the server is that process which provides a service to more than one user. And you can see how it's very often then that the user will initiate some activity with a server which has been listening, waiting for users. As a result of this initiation, packets will be sourced and sent to destinations, and data will thereby flow from sender to receiver. Now, we found that by attempting to use these common English words in the particular technical way that I'm suggesting, that some clarity comes in the understanding of packet protocols. So what I'm now going to describe is I'm going to try to use these words as consistently as I can. I'm going to describe a protocol which is mentioned in the Ethernet paper, which we call the Ethernet File Transfer Protocol, and thereby demonstrate something about the higher level packet protocols required both for the Ethernet and other packet transport mechanisms like the Ethernet. You may recall from one of the slides on the Ethernet Part 1 tape that Ethernet packets look like this, although I didn't draw it exactly that way. Make these dotted lines. This is 16 bits. Remember I mentioned that there was potentially some synchronization bits actually put on the cable, but those don't actually, in fact it's 1 bit in the case of our experimental Ethernet. Those bits are not actually put in the main memory of the computer which generates or receives, which sources or is the destination for a packet. They're affixed by hardware, so by special Ethernet controller hardware. For that reason I put them dotted, because they're not actually visible to the software which causes these packets to be transmitted and then receives them through the controller. I did, however, mention the destination and source, which I've shown here as two 8-bit bytes sitting in a 16-bit word, and this is literally how it looks inside the Alto, sitting in the Alto's main memory. Then I mentioned that there was some arbitrary number of 16-bit words in an Ethernet packet, followed by, and once again this is not evident in computer memory, but the Ethernet interface generates a 16-bit cyclic redundancy checksum, CRC, which is redundancy for the data in this packet, and that CRC is checked in the receiving hardware to see if any damage has been encountered in transmission. By the way, most of the time that damage takes the form of a collision. So now that if we have the Ethernet, and the Ethernet allows the transmission of packets that look like this, how do we, oh, and by the way, those packets don't always get to where they're going. In other words, I, as a computer program running in the Alto, in main memory, lay out a destination and a source and put a block of data in here and indicate to the Ethernet interface that it should transmit this packet. That packet will be picked up by the interface. The randomizations and all will occur. Eventually it'll get onto the coaxial cable, and eventually destination address will be recognized by the destination station. This packet will be copied into main memory. The question is, given that I can do this, and given that most of the time this packet will be correctly received, how do I organize myself? How do I organize my software so that these packets can result in a reliable data flow from the source to the destination? Well, we do this, and here's how we get into packet protocols, by putting some meaning on the bits stored in this packet. And in the EFT, the very first level assumption we've made in the Ethernet is this whole first word, 16 bits, we reserve for a type. That is, we have by convention determined that it's worth 16 bits of Ethernet packets to put an arbitrary bit pattern in there, which is to be interpreted as the type of this data packet. And we have a central registry of such types that we keep around, and associated with each type is a little document that describes the data in it. The EFTP described in the paper has 5 such types. There is data, acknowledgement, abort, end, and end reply. And these are the English words used to convey the semantics of these packets to you. That is, there is a number which, when plunked down into this 16-bit word, indicates to the receiving station of a packet that this is an EFTP data packet. There's another pattern which indicates an acknowledgement that it's an abort, an end, and an end reply. Now, given that we know which of these types of packet it is, there's now further meaning put on the words, the subsequent words inside this packet. In every one of these is a sequence number. That is, as the data packets are, let's say the problem is that from one station to the other we're going to transfer a file that's very large, say 10 million bits. We only allow the packets that we send to be very short, say in the order of 4,000 bits. There are a number of reasons why we don't make the packets arbitrarily long. One of them is we're sharing the cable, and we want everyone to get a crack at the cable now and then, so we keep the packet sizes short. 4,000 bits turns out to be our maximum size. Another reason for wanting the packets to be of limited size is that the longer they are, the more chance there is that they'll get struck by lightning and suffer an error. So there is some influence of error control which keeps you from having arbitrarily long packets. Yet a third reason is that these packets leave and enter buffers in the main memory of the computer. And it turns out that it's useful to have a fixed upper bound on packet lengths so that one can manage one's buffers in main memory carefully. So given that we have short packets and long data flows, we need to be able to packetize the long data flows, and in doing so we associate with each of the pieces a sequence number. And the sequence numbering is a very key idea in packet protocols. Another interpretation that we put on the bits in one of these data packets is we assign some number of words to indicate the length of this packet. You'll notice that the length of an Ethernet packet is not, there is no length number to indicate how long the packet is, and the way this is accomplished is when you hand a packet to the Ethernet hardware, you need to tell the Ethernet hardware how long it is, and it sends out that many bits onto the cable. And then as the packet's being received, the bits as they arrive are put into words and dropped into main memory, and then when the packet is handed over to the software, it's given a count of the number of words that were delivered. By putting a length field inside of this packet, what we do now is we have a confirmation. That is, we can look in the packet, and this packet claims to be of this length. How many words did I receive? And this is a way of checking that the appropriate number of words have been received. This also allows one to have words transmitted at the end of a packet which are garbage for various reasons of convenience. You just don't want to, your hardware can only transmit data, say, in quad word boundaries or something. You would tell the hardware about the big chunk of data, but inside you'd have to give some indication to the software of what the true size of this packet was, so only valid data would be interpreted. Then there's some number of words of uninterpreted data, and this would be the data coming from the actual file being transmitted. And then finally we have a checksum. You'll note that this checksum is not the CRC that I mentioned earlier, which exists only in hardware. This is a software checksum computed in software by the originating station and then checked by the receiving station to be sure that the data in this packet has been received correctly. This leads me to a point about error detection, which is very important in packet protocols. Here is some error detection in the Ethernet. This CRC is computed in hardware as the data is serialized and deserialized, and then it's checked in hardware. And here we have another error control mechanism. This one is a checksum over the packet's contents, which is performed on an end-to-end basis by the computers involved. You might immediately see that we now have 32 bits dedicated to error control, which leads me to one of my fundamental design principles of error control that I'm willing to share with you, which is when you're building a system, at first you should put in much more error detection than you would ever think is necessary. Then, having built a system and observed its performance and gotten some feeling about its error properties, it's invariably the case that you'll want to leave the excess error detection in, simply to give you constant reassurance that you haven't, that your system isn't broken. I hope you caught the irony in that. Put in too much and then leave it in later. Another thing you'll notice about this is that there are immense fields. You'll notice that the type field has 16 bits, allowing a total of 65,000 different type packets. And in this protocol, we've only used 5. Well, there are many other protocols, but certainly one could argue that one needs less than 16 bits of type field. But then again, there's the convenience in software of being able to manipulate the 16-bit word as a unit as opposed to doing some bit handling. The same goes for many of these other fields. It's invariably the case that when one attempts to be careful about defining fields of exactly the right length, one generally underestimates the need and has later to redo the entire protocol to take into consideration the fields that you've made accidentally too small. Now let's look at this checksum. Once again, computed over this. It's computed over the data visible in memory. The checksum for the EFTP is of a particular kind. It's 1's complement, add, and cycle checksum. That is, just before sending this packet, you call a subroutine pointing at this block and giving the number of words involved. And what we do is take this word and initialize the sum to 0 and add this word and cycle left, and add this word and cycle left, and add this word and cycle left, and add this word and cycle left over the whole block, and then store the result here. It's an add. It's a 1's complement add and with a cycle. And each of these characteristics explains a desirable feature of the checksum. First is this checksum must be efficiently computable by a 16-bit mini-computer, that is, the stations that we have involved. Well, 16-bit adds and cycles are operations quite conveniently performed by these 16-bit mini-computers. Second of all, it's desirable that the checksum be incrementally updatable. That is, if one were to change one of the data in this whole packet, if one had an incrementally updatable checksum like we do, one needn't perform this computation over the entire packet again, which incidentally remains a burdensome task. One simply needs to know what one is replacing this datum with, take out the old word, put in the new word, and there is a procedure whereby this checksum can be updated to reflect the change without recomputing it entirely over the entire length of the packet. A third desirable characteristic of the checksum is that it catch a lot of errors, that there not be frequent classes of errors that slip through, and that's the purpose of the cycle. By cycling, one takes bits and tends to mix. If there is an error, it will result in a lot of bits being different as a result of the cycle. For example, if there were a single bit error somewhere that was happening in 1 bit all the time, then it might happen due to luck that a 0 change to a 1 here might be compensated for a 1 change to a 0 here. But by cycling the data after each addition, we've reduced the probability that such a classical kind of error will go undetected. Now, the way this protocol proceeds is that data packets are sent with increasing sequence numbers, 0, 1, 2, 3. And for each one, an ACK comes back with the matching sequence number. And the next packet in sequence isn't sent until an acknowledgement is received. It is also the case that if the receiver receives a packet with a sequence number less than the one it's expecting, and this will usually be 1 less, then it needs to acknowledge this packet and throw it away. And that covers the case where a packet's been transmitted and the ACK's been lost. From the standpoint of the source of that data packet, it can't tell whether the data packet got lost or the ACK got lost, so it transmits the data packet again and then receives the duplicate acknowledgement from the receiver of this data flow. The abort packet, of course, is used to handle error conditions detected at one end or another. It's sent, an abort includes a reason inside of the data, a registered reason, one of several, for why a data flow file transfer would be aborted. The end and the end reply packets are used to solve a somewhat subtle and interesting problem. Say we're doing this flow from A to B, and we're now done with it. So an end packet is created, and the end packet has the next sequence number in sequence. And so an end is sent, indicating there is no more data to come. The protocol then calls for an end reply to be sent back. And the protocol also calls for this machine, having received the end and send the end reply, to dally. That is, it just sits there. Instead of going away, having completed the file transfer, it stays on the off chance that the end reply will be lost, in which case it will receive another end. So the purpose of dallying is to take care of the case where the end reply, the acknowledgement to the receipt of the end packet, is lost. Then there's a third exchange, which is another end reply. So when a dallying receiver receives an end reply, it can then safely go away, the transaction having been completed. So this end is a message from sender to receiver saying, I am done transmitting this data. The end reply, when received here, says, I now understand that the transfer is complete and that I have a complete file. And this final exchange says, thank you very much. It's now okay. I've now received your end reply confirming correct receipt of the file. You may now self-destruct. Okay, this is the very simple Ethernet file transfer protocol. And there are now, in the remaining minutes, I will now describe some of its deficiencies. The Ethernet file transfer protocol, as I've now defined it, is very simple. It has a number of deficiencies which is instructive to go over because they point at the direction of more sophisticated and complete protocols. One thing you'll notice about this protocol is that there are no new addresses defined. That is, the communicants in this flow are defined by the actual Ethernet destination and source addresses. A problem with this is that means a data flow must be addressed from a source station to a destination station. So for example, if you had a time-sharing system that was one station on the Ethernet and it had 10 or 15 jobs, then the data, if we only use this protocol, then only one transfer could be going on at a time from one station to another. That is, this whole huge time-sharing system would only be able to do one at a time. That is, there's no address extension here. So, for example, one might imagine elaborating this protocol some to allow one to address different points. That is, process 24 in the source station addressing process number 79 in the destination station, so that one could address multiple points within a station. Another way in which this address could be generalized would be to address more than just the stations on a single Ethernet, so that one might address a station on some remote Ethernet by giving the Ethernet's network number. So here's one area where this protocol is very simple and removes some generality. Another problem is that there's no, as we say, rendezvous in this protocol. That is, the destination station, even if we were to add address extension to this packet, there's no procedure in this protocol whereby the source and the sender and receiver find each other. That is, it's presumed that I'm going to send data to this one point. So for example, if there were a place that was willing to collect data from various senders, it would only be able to service one of them at a time in succession, one after another. If this protocol were elaborated to have a rendezvous protocol, then the first thing that the sender and receiver would do would be to negotiate another address on which this actual transfer of data would be performed, leaving the original address still free for repeated rendezvous and repeated settings up, so that multiple transfers could be handled concurrently. Another problem with this very simple protocol is that it has a very unsophisticated flow control mechanism. Data is acknowledged on a packet-by-packet basis. I send you a packet, you send me the acknowledgement. I send you a packet, you send me the acknowledgement. And you can see how that wastes the transmission facility, because I send you a packet and then I need to wait for that packet to get to you. I need to wait for you to receive the packet and figure out what it's all about, and then I need for you to generate an acknowledgement packet and for it to come through the transmission medium. All this time I'm sitting idle and the transmission medium is sitting idle. You could imagine, and this is quite common in modern packet communication protocols, where the protocol will allow more than one packet to be outstanding at once per acknowledgement, and that the flow of the number of such outstanding packets that I can have is controlled through the acknowledgement acknowledgments sent carry in them an indication of just how far ahead you can get in the process of sending these acknowledgments. Another problem with this protocol is that the length of the packet is indicated in units of 16-bit words, so that the data that you send have to be in units of 16-bit words. Unfortunately, it's quite common for files to contain bytes, 8-bit bytes containing characters. If that were the case, let's say there were 3 in one particular transfer, 1, 2, 3, there would be no way in the Ethernet file transfer protocol here to indicate that this is real data, this is real data, this is real data, but this is garbage, please ignore that, because the length unit is in units of words. So an improvement here would be to make the length in units of bytes, or perhaps even units of bits. One other deficiency is that in this case, the listener must be the receiver. That is, the way this protocol is so arranged, when data is going to go from point A to point B, that process begins by the transmission of a packet carrying data from point A to point B. So, for example, a listener can't be somebody who sends you data. It can only be somebody who receives data from you. And you could see how there might be instances where you'd want the listener to be someone willing to disgorge a certain file of data to you if you request it. So one might imagine putting a series of packet exchanges at the beginning of this protocol so that the direction of transfer could be decided, and the roles of listener and initiator needn't necessarily correspond with the roles of receiver and sender. Okay. In this tape, Ethernet Part 2, I've described 2 things. The performance of the Ethernet, and in just this minute I've completed describing to you the Ethernet's file transfer protocol. Both of these are included, one to show you that the Ethernet is able to transmit packets with high probability and with some efficiency, and the other of these, the protocol, is meant to show you an example of how such high probability of transmission system can be used to transmit data reliably. Of course, in the process of revealing this protocol to you, you've now been able to see several of its deficiencies. With that, I'll conclude remarks on Ethernet and refer you once again to the paper by David Boggs and myself, Bob Metcalfe, occurring in the Communications of the ACM, July 1976. Thank you very much.